Hi. So today we will learn properties of matter, magnetic properties of matter, and we will classify the substances as diamagnetic, paramagnetic and ferromagnetic substances on the basis of susceptibility and relative permeability. So here you have the value of susceptibility. Here chi, this is your susceptibility. And this is your relative permeability. If susceptibility lies in between -1 to 0, means it is negative for a given material, then that material can be categorized as diamagnetic material. Now if susceptibility is in between 0 and a finite number, a small finite number, positive number, then the material, that material is called paramagnetic material. And if susceptibility is very large, then that material is called ferromagnetic material. Now we know that relative permeability is 1 plus susceptibility. So do add 1 along both the sides and you will find the value, this value. So on adding 1 here you get 0 on this side. Relative permeability must be greater than equal to 0. And when you add 1 on this side, you will get 1. On adding 1 along this side, you get 1. So this is how the materials can be classified on the basis of their susceptibility and relative permeability into 3 categories as dia, para and ferromagnetic materials. Now, you will find that susceptibility of diamagnetic substances is of the order of 10 to the power -5. You can see in this diagram. Here, the order of susceptibility you can see is 10 to power -5. And in most of the diamagnetic substances, you will find the same. It is susceptibility is of the order 10 to power -5. Now, you will find that most of the coin elements like copper, gold, silver, all these have properties that of a diamagnetic substances. You have copper, okay, diamond also, and bright substances like mercury, lead, all these are your diamagnetic substances. In gases, this is nitrogen. And then silicon also is a diamagnetic substance. Whereas you will find that paramagnetic substances have positive susceptibility, but its value lies up to a finite number. So now if we take susceptibility, we know that your magnetization is equal to susceptibility into H. Therefore, magnetization upon magnetic intensity. And we know from before what is magnetization. Your magnetization, which is a vector, is equal to dipole moment per unit volume. Here Here M is equal to dipole moment. And that means current into area. Vector. So this is your magnetization. And magnetic intensity? Magnetic intensity of any magnetic material, like of solenoid itself. A solenoid produces a magnetic field B naught, that is equal to mu naught and I. Therefore, this quantity divided by mu naught, if you divide this quantity by mu naught, you get that the quantity is free from intrinsic property of material. Now it depends on all the extrinsic property, the current provided to the solenoid and the number of turns given to the solenoid. So on dividing magnetic field by permeability of free space, vacuum, you will get a quantity magnetic intensity H. So these are the quantities. Now let me come on the topic. So for a given substance, for bismuth, it is given as minus 1.66 into 10 to the power minus 5. And you may divide it by 1 also. There will be no change. And it is a dimensionless, unitless quantity. Dimensionless quantity because magnetization has same unit as magnetic intensity. So unit is cancelled. Now you can find that for 1.66 into 10 to the power 5, or better I should take the order only. For this magnetization, intensity is 1. Therefore, I have taken this value. For this magnetization, intensity is 1. Therefore, for one part, magnetization can be of order. I am writing only order, not whole value. Therefore, it comes equal to 10 to the power 5. So you find that there is decrease of one part of magnetization because you have minus value. So decrease. One part of magnetization of a material in magnetic field with intensity how much? With intensity with H is equal to 10 to the power 5 parts. So in this figure now you can find that when you place a diamagnetic material in any magnetic field, the magnetic field lines are expelled from this diamagnetic material. It suggests that it goes away from magnetic field lines. This is another way to say that its magnetization reduces. You have another figure. Here you can see that highest magnetic field is at the center, at this very point. So here diamagnetic material liquid has bulged out from this high magnetic field region, and it reaches its maximum at these places. Here the diamagnetic material are shifted from a region of high magnetic field. Now when the poles are far away from each other, then at the center you have region of small magnetic field. So you can see that diamagnetic liquid is gathered maximum at the centralmost point. Here is one more diagram. You have a diamagnetic material which has left this position in which the magnetic field is highest, and it is shifted along a perpendicular direction in which magnetic field lines are minimum through this substance, through its poles, two ends. So this is about diamagnetic material. When you place a diamagnetic material in external magnetic field, its magnetization reduces by 1 part in 10 power 5. And what is the reason behind? Reason of diamagnetism. Okay, so in a diamagnetic atom, one diamagnetic atom has no dipole moment. It is because in an atom, the two directional motion of electron is there. If one electron is revolving along one way and it has dipole moment due to its revolution in one direction in which there is external magnetic field, then the velocity of the electron ceases. Reduces, not ceases exactly, but reduces, velocity reduce because of your Lenz's law. Lenz's law suggests that when a magnetism arises, or when an electric current arises due to change in magnetic field, then according to Lenz's law, it will oppose the cause that has produced it. And the cause is your motion of electron along one direction. So it will be opposed, and so its velocity is reduced. Now another electron which has dipole moment along other direction. Suppose it has dipole moment along this direction, and you will find that its velocity increases when it is opposed to any external field. So dipole moment in opposite direction will be strengthened when it is placed in any magnetic field, and this is the cause of repulsion. So let me write it properly. Due to Lenz's law, the velocity of electron which produces a dipole moment in the direction of external magnetic field is seized or is reduced, and the electron which has dipole moment in the direction opposite to external magnetic field speeds up. So the substances, instead of getting attracted, the substances are repelled. Now all the substances have diamagnetism, all substances. But this diamagnetism is replaced due to it is very weak tendency, so it is replaced as very weak, so is replaced by para and ferro magnetism. Now your superconductors are perfect diamagnetic substances. And what is perfect diamagnetism? You may see in this chart that a diamagnetic substance has minimum susceptibility -1. So if susceptibility becomes -1, then that substance is called perfect diamagnetic substance. So superconductor have susceptibility is equal to -1. Now paramagnetic substances have susceptibility positive and a small value. And so you will find that in magnetic substances, magnetism increases. Magnetization by 1 part in 10 to power 5. So when magnetization increases, then you will find that on placing any paramagnetic material, this is your paramagnetic material, in any external magnetic field, then field lines get tinged inside the material. Field lines comes collected inside the magnetic material. This is your paramagnetic material. Also in second diagram you will find the paramagnetic liquid is shifted near to, it is attracted near to strong magnetic field position. Here magnetic field is strongest between North Pole and South Pole. As they are very close to each other, so this material you can find that is highest at this middle point. Whereas when you displace this external North and South Pole, here you have minimum magnetic field, B minimum. So the paramagnetic liquid is shifted from minimum magnetic field position to a position where magnetic field will be highest. Here you can see that when you freely suspend a paramagnetic material in magnetic field, it will try to arrange itself in a direction where magnetic field is highest. Here it has shifted parallel to magnetic field. So this was all about paramagnetic material. There are some examples I have shown already. Calcium, sodium, chromium, all these are paramagnetic materials. And also gas, oxygen, which is at STP, is also a paramagnetic material. Now paramagnetism and magnetization does not wholly depend on magnetic field, external magnetic field. It also is proportional to, inversely proportional to absolute temperature. And giving a constant of proportionality, you will find that it is equal to CB upon T, where here C is Curie constant. B is external magnetic field. T is your absolute temperature or temperature in Kelvin. And M is your magnetization. And this law is called Curie law. So magnetization of a diamagnetic substance does not wholly depend on magnetic field, external magnetic field. Rather, it also depends on temperature. So though a diamagnetic atom has a dipole moment, but due to random thermal motion, magnetization becomes equal to 0. So when you decrease the temperature considerably and when you increase magnetic field to a high value, then you can observe magnetization. In diamagnetic substances, ferromagnetic materials have very high susceptibility, greater than 1000. I am showing you some ferromagnetic materials. Here you can see, instead of ferromagnetic atoms, there is large size. Here you can see you have large size volumes which have magnetization in one direction. These volumes are called domains. So in ferromagnetic materials, instead of having ferromagnetic atoms, you have domains, large size domains. So what are domains? In a ferromagnetic atom, there is permanent dipole moment. Now these dipole moments arrange themselves spontaneously, अपने आप spontaneously along one direction over a macroscopic volume. Of thickness for example 1 millimeter and having atoms 10 to the power 11 in number, and such volume is called domain. It is called domain. Now, when these domains, which are in different directions, arranged in different directions, so net magnetization net is equal to 0. But when such material is placed in any external magnetic field, two things happen. Firstly, the domain arrange themselves in the direction of magnetic field. And yes, one more thing here, this in per domain in which magnetic dipole moment is arranged in the same direction, this effect is called exchange coupling. Exchange or you can also say this as a cooperative effect. So all the atoms arrange themselves in the same direction of dipole moment, and this effect is called cooperative effect, exchange coupling or cooperative effect. Now, when they are placed in external magnetic field, two things happens. Number one, the domains align themselves. And second, they grow in size. And finally become a single large domain. Now we have examples of ferromagnetic material like iron, cobalt, nickel, and you have alnico, and Ly is also a ferromagnetic material. You have gadolinium. You have gadolinium. Or you have natural magnet or lodestone. So all these are examples of ferromagnetic material.